Hi guys, welcome to the next lecture. So we were talking about relations on any particular set or between two sets. When we started the topic of relations, I told you guys that relations could be of three types: reflexive, symmetric, and transitive. We've spoken about reflexive relations and terminologies around it. We've spoken about symmetric relations and terminologies around it. Today is the time when we will talk about transitive relations. What is the meaning of transitivity? So transitivity, the word transitivity comes from transit, right? So transitivity means, let's think in terms of a very general relation. So I live with my husband and my daughter. My husband is the tallest. I am shorter than my husband and my daughter is shorter than me. Don't you think logically and automatically my daughter is shorter than my husband, right? So the relation is transiting. It's a transitive relation. In general, if say you have A, B, C, and we are taking the relation is shorter. Say B is shorter than A, and C is shorter than B. Automatically, you would realize that C is shorter than A. That is, A is the tallest, right? This picture gives you the same logic. Hence, a relation R on a set A is said to be transitive if A comma B belongs to R and B comma C belongs to R. Then, if this is happening, then A comma C belongs to R. In other words, ARB, BRC implies, and when I write comma here, that means and, both the things are happening together. That should imply that ARC. That should flow logically. Now, some relations could be transitive and some relations might not be transitive. Suppose we take the set of natural numbers as our set A and we define a relation successor. So in terms of natural numbers, is a successor is my relation. Now clearly 3 is a successor of 2 and 2 is a successor of 1. But can you say that 3 is a successor of 1? What do you mean by successor? Successor means exactly the next number. So successor basically means n plus 1, next number, okay? So 3 is not a successor of 1. So 3 doesn't come immediately after 1. So hence this is not a transitive relation. So when you are learning about transitivity, it's important to understand what is not transitive. Clearly, the relation defined like this is not transitive. Let's understand transitivity with more examples now. I'm taking a general set A, which consists of 3 numbers, 1, 2, 3. And these are the relation sets that I have created. Let's figure out whether these sets are transitive, whether this relation is transitive or not. So what do we have? We have 1, 2, 2, 1, 1, 1, 2, 2. Now 1, 2 and 2, 1 could be connected together. If this is A, this is B, and this is C. This is A, this is B, this is B, this is C. Then I should have a combination AC, which would mean 1, 1. And that's happening, right? But we also have 2, 2 in the set. Do you think 2, 2 could be linked somehow? Well, let's try it. Let's check. So if you take 2, 1 first, and then you take 1, 2. So this situation becomes like, this is AB, this is BC, So AC should be there. And clearly AC is there. AC turns out to be 2, 2. And 2, 2 is a part of the set. So therefore, the all possible combinations when you take of A, B, B, C, and you got to check AC is happening or not. That's happening here. So this is a transitive relation. What about this relation of the diagonal entries 1, 1, 2, 2, 3, 3? Is this a transitive relation? Let's take into consideration. Let's take into consideration 1, 1. In order for me to be able to check for transitivity, what do I require? What is the prerequisite? The prerequisite is, in case A are B and B are C, that should imply A are C, right? In case A is related to B and B is related to A. Now, in this A and B is related to some C. In this set, is there any entry which is starting with 1? Because my B is 1. Is there any entry starting with 1? No. So that means my hypothesis actually is not getting satisfied. There's nothing to prove. I would prove the implication only when of transitivity, only when the prerequisite is getting satisfied. The prerequisite is not happening only. So there's nothing to prove in it. So we will be taking this relation as a transitive relation because you cannot actually prove that this relation is not transitive. Even for not transitive, what do you require? You require the prerequisite to happen, and then the result is not happening. Here you have A, B, B, C, C. To be able to say, comment anything on transitivity, you require with AA, you would require something which starts with A. Nothing is starting with A. So the prerequisite itself is not getting satisfied. Okay. This is a transitive set because I cannot prove that this is not transitive. Similarly, suppose you have a relation given to you like number 3. You just have one entry, 1, 2 here. There is nothing to prove because I don't have any other entry here. 1, 2. But I don't have any entry which is starting with 2. So there's nothing to prove here, and I cannot even disprove that it's not transitive. So hence we will take it as transitive relation. 1, 2, 1, 3. Now 2 entries are there. But in order for me to be able to check for transitivity, I got to have, in case I start with 1, 2, I got to have something which starts with 2. That's not happening. So nothing to prove there. If I take 1, 3, then I need something to start with 3. It's not there, so nothing to prove. Hence, this is also transitive. 1, 2 and 3, 2. Again, do you have a combination which will satisfy the prerequisite? No. So there's nothing to prove here because my prerequisite itself is not getting satisfied. So I will take it as transitive. I cannot even prove that it's not transitive. So that is the reason why we will take this as transitive. Now suppose you have 1, 2, 2, 3, 1, 3, 1, 1. Then what's going to happen? 1, 2, 2, 3. If I start with 1, 2, do I have any entry which is starting with 2? Yes, I have 2, 3. When 2, 3 is happening, is the entry AC, that is 1, 3 there? The truth is yes, it is there. So yes, it is happening. Now, can I use transitivity prerequisite in any other combination? Well, if you start with 2, 3, is there something which is starting with 3? No. If you start with 1, 3, is there something which is starting with 3? No. If you start with 1, 1, is there something which is starting with 1? Yes, 1, 2. And in this situation, this is your AB. Okay, let me just throw some more light on it. Hence, I'm continuing here. So you take 1, 1. Is there something starting with 1? Well, yes, 1, 2 is starting with 1. So this behaves like A, B. A is related to B. B is related to C. Then A should be related to C. A is 1. C is 2. 1, 2 is there, right? So A, R, C is happening. Similarly, actually with 1, 1, I also have 1, 3, which I can relate to. So both of them together should be giving me 1, 3, and that is happening. So therefore, this relation is actually transitive. We have covered all possible combinations. What about the set 3, 1, 2, 3? So you have 2 points here, 3, 1. 3 is related to 1 and 2 is related to 3. Let's see what we can do. So 3 is related to 1. Do we have any entry which is starting with 1? Well, no. There isn't any such entry. So we don't need to check anything there. We have 2, 3. Is there any entry which is starting with 3? Well, yes, 3, 1. So I'm going to write 3, 1. I can make a combination. So what is happening here is that you do have A, B, and B, C. What is the requirement for transitivity? In case this is happening, then this should imply A, C. That means 2, 1. But that's not happening. This is not a part of the set. So therefore, this is not transitive. This relation is not transitive. Which relation is not transitive? I gave you a general example. Earlier, I gave you an example with natural number of successor. And here, I've given a relation set in which that third ordered pair is not there. So in case the prerequisite is happening, but the final result, the implication result is not happening, then a relation is called intransitive or not transitive, in other words. There is one very important thing which you must take away from this example that we've done. The pairings could be in any order. So since it's written 3, 1 first and then 2, 3. But I can take the pairing as 2, 3 and then 3, 1. So pairings could be in any order. It could be B, A, B, and B, C. That should imply A, C. But the pairings could be, you can take any ordered pair first and, any ordered pair in the given relation as second. Let's understand transitivity more generally. Suppose X, Y, Z, as you can see here, I've written, these are 3 points. And there are paths along these points. That is, I have a path with which I can reach Y, point Y, X from X to Y, and I have a path with which I can reach Z from Y, if that is happening. And if I get a path, a shorter path with which I am able to reach directly from X to Z, then this relation would be a transitive relation. You have a longer path, a longer way to reach certain point, and you also have a shorter way to reach directly to that point, then the relation is transitive. I'm trying to say is that if the relation is transitive, then you have a short path as well. If the relation is transitive, then you have a short path as well to reach this point Z. But this might not happen always. So hence some relations can be transitive, some might not be transitive in nature. Okay, so let's try to make it interesting and let's now take examples of the set of natural numbers and talk of all the 3 concepts: reflexivity, symmetry, and transitivity. Okay, so first let's look at strictly less than, the relation strictly less than. Take any natural number. 1 is lesser than 2. 2 is lesser than 3. And 1 is definitely lesser than 3, right? So this is a transitive relation. strictly less than is definitely a transitive relation, because this will happen with any general ordered pair that you take. Any two general ordered pair that you will take in terms of natural numbers, natural number 1 is lesser than natural number 2, natural number 2 is lesser than natural number 3, and that would definitely imply that natural number n1 will be lesser than natural number n3. Okay. What about less than or equal to? With less than or equal to, let me start with the concept of reflexivity. So is this relation reflexive? Absolutely. Because any number is less than or equal to itself. Any number. X is less than or equal to x for all x belonging to the set of natural numbers. Okay. Now, is this relation symmetric in nature? Well, 1 is less than or equal to 2. But is 2 less than or equal to 1? Well, absolutely no. So this is a reflexive relation, but not a symmetric relation. What about transitivity? Is this a transitive relation? Yes, it is. So 1 is less than or equal to 2. Then I need something which is starting with 2, right? 2 is less than or equal to 3. And yes, of course, 1 is less than or equal to 3. In case you take equal, so 1 is less than or equal to 1. It falls in the equal category. 1 is less than or equal to 1, and hence 1 is less than or equal to 1. So if you just have 1, then also, you're always just working out with the diagonal entry, the only diagonal entry, right? So this is transitive. Less than or equal to is reflexive and transitive, but it is not symmetric. Let's take further a more interesting example. Let's take the relation as x minus y. The difference between two numbers is not equal to 0. Again, we are dealing with natural numbers. Will this relationship be reflexive? Now, reflexive means that x should be related to x itself, which would mean that x minus x should not be equal to 0, because that's the relation, but that's a contradiction. How is that possible? X minus x is definitely equal to 0, and that's true for any natural number. This is true for any natural number, right? This is not a reflexive relation. What about symmetricity? Is this a symmetric relation? Okay, so let's talk about pairs. So if you talk about 4 minus 3 is not equal to 0. And yes, that implies 3 minus 4 is also not equal to 0. So we do have 4R3 and 3R4, both are happening. So it seems like it is symmetric, right? Now I'm going to take you through another example here. So what about 4, 4? Now, 4, 4, that is 4 minus 4, is not equal to 0. Does that imply 4 minus 4 is not equal to 0? What I'm trying to tell you here is that you have, say, x, y, they're equal. That is, you have xrx or you have xry. Is xry implying yrx when I'm taking a case that x is equal to y? Okay, so this is what you want to check. You want to check. Now the fact is that 4 minus 4 is not equal to 0 is incorrect. 4 minus 4 is in fact equal to 0. So 4 minus 4 is not equal to 0 is a false statement. And the thing is, with implication, an implication is an if and then statement. What are we saying in this implication? If 4 minus 4 would not be equal to 0, then 4 minus 4 should not be equal to 0. Now 4 minus 4 is not equal to 0, is false. Actually, because 4 minus 4 is equal to 0. But this statement is saying that had it been a case, if 4 minus 4 would not be equal to 0, then 4 minus 4 would not be equal to 0. This is true. When actually the hypothesis itself fails, the hypothesis is false in a conditional statement, you assume the statement, the conditional statement, to be true because you cannot disprove the statement. In order to disprove, this is an if and then statement. If this happens, then this should happen. If part is not happening, so that means you cannot really disprove the statement. Okay, well, we will talk about all this in mathematical logic soon. But for now, this statement is actually true even if I take 4, 4 as a part of this relation. So which means it is a symmetric relation. Why I took it? Because set of natural numbers consist of everything, right? So even 4, 4 would be a part of it. So this is a symmetric relation. It indeed is a symmetric relation. What about transitivity? Will it be transitive? For transitivity, what do you require? You would want to actually prove, I'm writing TP for to prove, I would want to prove that x minus y is not equal to 0. So this is like xry. Hence, I would want yrz in order to check for transitivity. So yrz would be like y minus z is not equal to 0. And that should imply that xrz, which would mean that x minus z is not equal to 0. Well, will that happen? Let's take any example. Say, let's take 3 minus 4 is not equal to 0. Right, absolutely right. What if I take 4 minus 3 only? 4 minus 3 is also not equal to 0. But mind you, this is giving me scenario where this is your x, this is your y, this is your y, this is your z. So x and z are actually equal, but 3 minus 3 is actually equal to 0. So therefore, what's happening? This is intransitive. So xry, yrz, but not of xrz is happening. So therefore, this is an intransitive relation. That is, it is not transitive. So this is an example of a relation which is reflexive, not reflexive, symmetric, yes, but not transitive. Let me take a new relation now. Let's take the relation x equal to y. So xry is defined by x equal to y. Let's check for reflexivity. Is this relation reflexive? For reflexivity, I need to check xrx. X is equal to x, yes. So of course this is reflexive. Is this symmetric? For that, what do I require? I require x equal to y, then y should also be equal to x, and absolutely that will happen no matter what number you take, because you're talking about equality. What about transitivity? For transitivity, what do I require? If x is equal to y and y is equal to z. Now x is some number which is equal to y. That means, 1 comma 1 or 1 is equal to 1. And y is also 1. So 1 comma 1 again. That will give you 1 comma 1. 1 comma 1 is already there. That would definitely imply x is equal to z. Basically, x, y, z, they're all equal, right? This will always happen. I've taken a general example. You can take numbers and figure it out. Of course, this will always happen. So this particular relation equal to is a very special relation. It is satisfying all the 3 properties: reflexivity, symmetry, and transitivity. Equal to is very special, is special as it creates something called an equivalence relation. What is an equivalence relation? A relation which is all 3. That is, it is reflexive and symmetric and transitive. A relation which is satisfying all the 3 properties is called an equivalence relation. And that's what equal to is creating. Thank you.